All right, good morning, everybody. Today I want to talk to you about graphical analysis, and I'm going to start with a slide that I showed you in the last video. We talked about the historical gas laws, which are shown here. They relate these macroscopic variables, volume, pressure, temperature, to one another. And the question really is, how can we analyze these principles, these ideas with a graph? And here's what that would look like. I swear to you, you think I could click the down key, but it just doesn't seem to be working. It drives me crazy. There, now it finally worked. Okay, so on the left, we have Charles' law, which tells us that volume is proportional to temperature. If I plot volume on the y-axis and temperature on the x-axis, I get a straight line. And as you may remember from your general chemistry course, if you extrapolate this one back, you will hit absolute zero. This is another version of it. Charles' law also tells us that pressure is proportional to temperature. Same sort of game. If you extrapolate these lines backwards, you hit absolute zero. Last but not least, on the right, we have Boyle's law. Boyle's law told us that pressure times volume is a constant. So pressure on the y-axis, volume on the x-axis. If volume is really big, the pressure is small. Vice versa, if the volume is really small, the pressure is really big. So these are called hyperbolas. And you can see then as you increase temperature, you move out this way. One of these plots is actually going to end up being relatively important throughout the semester. We'll talk about them a lot as we move into the next chapter, and it's this one. These lines of constant temperature have a specific name, and they're called isotherms. And you're going to work a lot with these throughout the semester. Now, we can use this idea of graphical analysis to learn important things, specifically in calculating R, the ideal gas constant. So what I'm showing you here on this slide are real molar volume data and pressure data for carbon dioxide at 20 degrees Celsius. Okay, so this is experimental data. You can look it up at this website. And the question is, given this experimental data, how would you calculate R? And let me suggest one possible way that you might consider. Let's see if I can get my pen to work. Here's how you might do that. So I can take the ideal gas law. I solve this for R. This gives me a simple equation which I could plug and chug and calculate R, right? And if I do that, here's what I end up with. So I get all these values of R. Up here at high pressure is 0.05 liter atmosphere per mole K. Down here I get 0.08. You can see that that value varies by quite a bit. And you might have an experience like this with your experimental data. I would expect that the ideal gas constant should be constant. So maybe this is just experimental error. And the way you might handle that would be then to calculate an average, right? I should probably put a line over this, right? This is the average R. If I took all those values and I calculated the average R, you'll find that it's 0.068 plus or minus 0.004 liter atmosphere per mole K. My neighbor's walking by. You compare that with the literature value, and you'll see that they don't match. R is 0.082. We're off by a lot, like 30 or 40%. Right? So this isn't a really good approach to do it. We need something else. Here's another way that you might do it. I'm going to assume that R is 0.082 liter atmosphere per mole K. And I'm going to make a graphical plot, a Boyle's law plot. So I put P on the y-axis and the volume on the x-axis. Solid lines here, sorry, the solid points are the experimental data points. The solid line is the theoretical prediction based on the ideal gas law if I assume this value. And if I were to look at this data point, or this plot, I might say, boy, this is really a good fit. It's really close. It looks really dead on. And you can even do fancy things like calculating the R squared value. Okay? It's pretty good, 0.097. However, it turns out that this is also really inadequate. If you happen to take a general chemistry lab with me, Chem 119, you may remember that I hate R squared. I think it's the most misused statistic in the world. And this is part of that reason. But anyways, this also doesn't work, and let me show you why. So this was my postdoctoral advisor. His name was David Nesbitt at the University of Colorado. Oh, geez. That's my phone. Hang on a second. And what David used to say is that all science can be reduced to a straight line plot where we interpret the slope or intercept. We want to make everything a straight line plot where we interpret the slope or intercept. Dr. Nesbitt is a friend of Dr. Yokoyama, so if you know Kazu, you can ask him about David Nesbitt. If I take this idea, right, and I think about how I could work with the ideal gas law in order to make it a straight line plot, this is what you might do. Where'd my cursor go? No one knows. There it is. P equals nRT times 1 over V, okay? In other words, this is looking like a straight line plot. Y equals mx plus b. And this will turn out to be another important way to visualize some of this pressure volume data, okay? This is what that would look like, right? I put pressure on the y-axis, and I put 1 over volume on the x-axis, right? Again, this predicts that I should get a line which goes through 0, so I should extrapolate out and get 0. And the slope of this line is related to the ideal gas constant. All right, I'm finally set to answer that initial question, which is how do I calculate R? I'm going to do it using a straight line plot where I interpret the slope or intercept, and here's what that looks like. Right? Again, solid data points are the experimental data points, or solid symbols are the experimental data points. This is the theoretical prediction from the ideal gas law. And you can see something really interesting. Okay. What I would predict is that I should get a straight line which goes through 0. And you can see that down here in this region, that's basically true. Right? When 1 over volume is really small, in other words, when the volume is really big or the pressure is small, gases behave ideally. Straight line that goes through 0. I can look at the slope of that straight line, 23.4 plus or minus 0.021. You can calculate uncertainties in these numbers. You'll find that they're dead on. And from that slope, again, I can use that to calculate R. And if you do that, what you'll find is that R is now 0.080 plus or minus some small amount. It's actually within the accepted value. So this is a really effective way, an important way to analyze data. Right? It also reveals something which is really interesting. This is my cliffhanger. Down here, gases behave ideally. But up here, gases are not behaving ideally. They are non-ideal, okay? I would predict that gases would exhibit a much higher pressure than they in fact do. So the question is why? Why aren't gases ideal? And I'm going to leave it here. You can think about that. You can think about the assumptions in the ideal gas model and what might be going on in this region that would cause this behavior. So you'll have to check out my next video. All right, so here's my moral of the story on graphical analysis. Whenever possible, analyze data graphically. Like David Nesbitt says, create straight line plots where we interpret the slope or the intercept. And if you'll notice this, if you were looking carefully, you'll notice that I always put units on my axes. Incredibly important. It's really, really important when you're analyzing slopes or intercepts. All right, that's all I got. So I will see you next time for a discussion of real gases.